So you remember we left off last time, we were talking about the t distribution. So we have a new distribution that we have to look at. We will need to pull numbers off of this distribution. It will work an awful lot like how the normal distribution worked. In fact, the t distribution is kind of a uh, more pronounced version of the normal bell curve. The tails are wider. Here's a few examples of different t distributions. The normal curve, it's maybe not super easy to see. The normal curve is in blue here. So the normal curve is taller and a little bit more slender. The t distribution is a little bit shorter. It's like someone just pushed down on the top and widened it out a little bit and shortened it. So the t distribution has larger tails. It's fatter in the tails, if you will. But for practical purposes, we need to use the t distribution whenever we are making a confidence interval for a mean, and we do not know the distribution of the population that our sample came from, and if we have a small sample size under 30. That is basically going to be our hint, our cue that we need to use the t distribution. It changes based on the degrees of freedom. And remember, the degrees of freedom is the sample size minus 1. So it's a new variable we're talking about, but it's very easy to remember. Whatever the sample size is, subtract 1, and that's what the degrees of freedom are. You'll use the degrees of freedom whenever you're looking up values from the t distribution table. Just like the normal, it's centered at 0 if you're talking about the standard normal, and also symmetric about 0. Just like all probability distributions, normal or otherwise, the area under the probability curve or function is 1. Because of the symmetry, half of that area is to the right of 0, half is to the left of 0. And also the x-axis, if you will, is a horizontal asymptote. It's really cool. As you get larger and larger sample sizes, the t distribution kind of bucks up here and gets closer and closer to just being the normal distribution. And that's actually something that is true in theory if you had some, advanced math background, that you could prove that using functions and whatnot. So be careful, it cautions. The t table reads totally different from the z table. Whenever you use the t table, what you're going to do is you're going to look up things on the t table according to the degrees of freedom you're dealing with. Then you're going to have to decide what probability you're looking for. And then inside the t-table is the t-score you want. So it works completely differently from the z-table. On the z-table, you use the z-score you want to look up an area. On the t-table, you look up specific areas and find the corresponding t-score. So it's a completely kind of different table altogether. And that's just because whenever you have to deal with both degrees of freedom and area, that's two variables, and you just can't make a table that has a ton of information on it. Whereas for the z-table, you only have one variable you're cross-referencing. So what we're going to do is we're always looking for the area in the right tail, just depending on what chart you're using, or what you want for your confidence interval. And it's actually probably a little bit easier to work with. It's probably a little bit easier to work with. So let's try this. I have a t-chart handy. Let me open that bad boy up. Here. Boy, guys, I know this is completely off topic, but I am just super excited for Christmas this year. Is anyone else excited for Christmas? I hope you are. Hopefully you can just feel the excitement in my voice because Christmas is a lot of fun. And let's see, did anyone comment? Oh yeah, yes, Ryan. Very much excited for Christmas, Tira. I can't wait. I think we really need Christmas this year, not just because of the pandemic has just kind of made everyone, I don't know, sadder. Uh, but that is certainly a big part of it. I won't deny that. Okay, so find the t-value such that the area under the t-distribution to the right of that t-value is 0.2 with 10 degrees of freedom. That is, find t sub 0.2 with 10 degrees of freedom. It's not as hard as it sounds or as complicated as it sounds. The degrees of freedom are 10. The area to the right that we're looking up along the top column is 0.2. So all we got to do, and now I'm pulling up the same T chart you're using in your homework so that we have some nice consistency. So all we got to do, we look up 0.2 on this top part. That's the area in the right tail. Notice there's only a handful of values. I can't look up any area I want. I can't just look up 0.3461 or, 0.0198. I'm limited. I'm fairly limited in the areas I have choice from. And it's just because we can't put every t value necessary on the chart. It's just, quite difficult to do that. But anyways, we have 0.2 is the area we want in the right tail. Then we cross-reference that against 10 degrees of freedom. And here it is. Here is our lovely, lovely t-value of interest, 0.0879. So that is the t-value we want. We're going to be using that shortly here in order to calculate confidence intervals. So 0.0879. And there it is. That's our t-value of interest. A more apt problem. Find the critical t-value that corresponds to 98% confidence. Assume 16 degrees of freedom. So remember, and I'm going to draw the tails to be a little larger than they really would be in this case. 98% confidence means we want 98% in the middle with Malcolm, or 0.98. That means we've left 2% on the table. We've left, if there's 98% in the middle, we've left 2% for the tails. But there's two tails and they're symmetric. So we need to divide that by 2 to figure out how much belongs in each tail. And so that's clearly 1%. And so there's 1% that belongs in this left tail, which can be written as 0.01. And partner, there's also 1% in this right tail. And so this is the t-value we are wanting to use. The t-value is right here It's the t-value that has 1% in the right tail. So we want t for 0.01, and then you'll see this semicolon for 16 degrees of freedom, which that's just straight up what the problem is telling us. All right, so we want 1% in the right tail, or 0.01 in the right tail. So suddenly we are looking on this column here because 0.01 is the area in the right tail. Then we scroll down until we found 16 degrees of freedom, cross-referencing it here and here. On your homework, you can play with that a little bit more. And so that's going to be 2.583. Yep, 2.583. 16 degrees of freedom, 0.01 in the right tail. 2.583 is our t-score. So I'm going to have to remember that. 2.583, 2.583. So yeah, you just have to cross-reference degrees of freedom. So arguably, the chart is a little bit easier to use. The chart is arguably a little bit easier to use in a final analysis. Well, get used to doing that, because if you're making t confidence intervals, you're going to have to remember how to do that. Really, the confidence interval is not difficult. You get a nice formula for it. The hardest part is finding the value of your statistic, or the value from your probability distribution that you need. So, bringing it all together to save you more, constructing a 1 minus alpha times 100% confidence interval for mu. You would only do this if the sample data come from a simple random sample or randomized experiment. You don't have to worry about that. That's, good. That's going to be the case for our purposes. The sample size cannot be too large, though. So we want the sample size to be less than 5% of the population. That's all that means there. Fancy magic terms. We want the, this is not quite accurate. We would normally love the data to come from a population that's normally distributed, or the sample size is large, but if you don't have that, you can still use the t-distribution. So if the data came from a population that's normally distributed, or we had a large sample size, we could actually use a z confidence interval. We could use a z-score here instead of a t-score. It turns out, though, even if you have that, you can still use the t-score. That's why it's so nice. The t-distribution is robust. If you have a small sample size and you don't know where your population came from, you can still construct a t confidence interval for the mean. You can still do that. So all you're doing, you're going to be given a sample. It's going to be a bunch of data values. You could be asked to find the confidence interval, a 95% confidence interval for the mean. So you need to calculate x bar, which is the mean of the sample, x bar. You need to calculate S, the sample standard deviation. You also need to find the relevant t-score, and you need to just know what the sample size is. This formula is provided to you on the final exam as a formula sheet. You'll need to print it off beforehand. So everything over here, the part after the plus or minus, is our margin of error. And we just need to remember the degrees of freedom is the sample size minus 1. But in this calculation, we still just use the regular sample size. We just need to know the degrees of freedom to look up the proper t-value. So let's have a fun confidence interval computation here. Listed below are the brain volumes, which is kind of a weird thing, but listed below are the brain volumes of subjects used in a study. Now I'm going to have to make this a little bit larger. Assuming a normal distribution, find a 95% confidence interval for the mean brain volume of the population. So we're going to use a T confidence interval. We're going to use a T confidence interval. Here's a few things we can put. In the sample size, well, just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the sample size is 10. The degrees of freedom is just a sample size minus 1. So the degrees of freedom is 9. Now, X bar and S, well, this is chapter 3 material. If you remember good old chapter 3. And so you should have a system for figuring out the mean and standard deviation of a sample by now. You can use your calculator, put the 10 data values into your calculator, which is what I'm doing right now. I'm working it with you. Here we go. We got 10 values. And I'm seeing a mean of 1130.2. In fact, I seem to remember that we did that calculation last time. Should be getting a mean of 1130.2. Now I'm going to find the sample standard deviation. Again, there's a lot of very wonderful little tricks that you can use, calculator tricks, where you can just put the data in and have it calculate those statistics for you. We kind of went over them in chapter 3, and I pointed you to some videos you can find in the Canvas modules for that. But it looks like the sample standard deviation, I'm going to round it to 2 decimal places, is 117.45. 117.45. So our T critical value, we need to use the T chart. But basically, we want 95% confidence. So there's 0.95 in the middle here. That leaves 5% for either tail. 5% divided by 2 is 2.5%, or 0.025. That can go into each tail. .025 that goes into each tail. So you'll want to use your T-chart. Now, if you have your online homework open, you can pop open the T-chart there. You know how to look it up. You need to look up along the 9 degrees of freedom row, and then you need to look at 0.025 along the top row and find the corresponding T-score. Unfortunately, if I bring it up on my end and show you, for some reason it's deleting text today. So lots of fun, but you can look it up too, and then we can confirm. The T-score I'm getting is 2.262. 9 degrees of freedom, 0.025 in the right tail. Be careful because there's also 0.25, which is 25%, which is 10 times too much. So just be careful. Make sure to read your decimal place carefully. There's also, confusingly, 0.0025, which is way too small. So Papa Bear's porridge was too warm. Mama Bear's porridge was too cold. But let me tell you here, Pilgrim, 0.025 is what you're looking for along the top row. And you end up with a t-score of 2.262. 2.262. So now, partner, you got yourself all the ingredients to make your confidence interval. I'm going to have to scroll down. Let me fix all the values here, because everything scrolled with it. Return from whence you came. You as well. Let's see. Be tactful about this. There we go. Now everything's back to where it was. I just needed more space down here. Our confidence interval is going to be x bar plus or minus the t value we found times s, the sample standard deviation, over the square root of n. So let's plug and chug with what we've got. 130.2 plus or minus the t value, 2.262, times 117.45 divided by the square root of n is 10. So don't put the degrees of freedom in there, still put n itself. Now, to actually do that computation, I will compute the standard deviation here. Or excuse me, I'll compute the margin of error. All right, so the margin of error that I've found, this confidence interval will be 130.2 plus or minus, that's how you write plus or minus, on the keyboard. The margin of error is 84.013. So we do 1130.2 minus 84.013. That will give us a lower bound of our confidence interval of 1046.187. That's the lower bound of the interval. The upper bound of the interval, we do 1130.2 plus 84.013. And we'll have 1214, the year I was born, 0.213. And there you have it, folks. We have computed the confidence interval that we will be using here. So this was a 95% confidence interval. We can say we are 95% confident that the true average brain volume is somewhere between 1046.187 and 1214.213 cubic centimeters. That's what we'd say. And remember to say you're confident. You're not saying there's a 95% chance the average brain volume falls in this range of values. really what you're saying is that if you were to go out and take samples of 10, use a sample of 10 brains, then do it again, then do it again, then do it again, then do it again, and you kept making confidence intervals for each sample, you would capture the true mean 95% of the time. 95% of your confidence intervals would correctly capture the true average of whatever you're talking about, in this case, brain volumes. So it's kind of an interesting idea. Again, it gives us a range of values. Now, theoretically, if you want a 100% confidence interval, well, I'll give you a 100% confidence interval. I'll bet you that the average brain volume is somewhere between negative infinity and positive infinity. Not very helpful, is it? So 100% confidence is the most arbitrarily wide interval possible. That's why we don't talk about 100% confidence. We really just can't. 100% confidence is, well, I bet you your height is going to be between negative infinity and positive infinity. Yeah, I bet it will be. Thank you for that. So we have to limit ourselves just because of the probability distributions we're using. The only way to capture 100% of the area under the curve is to go to all the way down to negative infinity on your score, all the way up to positive infinity on your score. That's the only way. So, kind of an interesting conundrum we find ourselves in statistics. If you want to calculate the sample size needed to estimate the population mean with a given margin of error, I won't focus too horribly much on this. There's a simple formula for it. You're assuming the reason we're now using a z-score here is because we're going to assume that n is going to come out to be a really large number. So if you want to capture a certain confidence level or a certain margin of error to keep your confidence interval so narrow, you're going to end up needing a sample size so large that the normal distribution would have kicked in. So you're going to use a z-score there. You multiply it by your sample standard deviation, divide by the margin of error, and then square all that. We won't go into uber detail about it. To be honest, this isn't something, this is debatably good statistics work here. It's hard to say. Certainly they love to teach about it in classes, but what you're doing is you're making assumptions before the fact about things that are going to happen that can only make sense after the fact. So it's kind of not good science, not good statistics, in my humble opinion. Okay, so we have finished up chapter 9, actually. Chapter 9 was entirely concerned with confidence intervals. Confidence intervals were our major theme of chapter 9. And now we get into chapter 10, and we really do just save the best for last in this course, because the material we're going to get into in chapter 10 concerns something called hypothesis testing. And as it turns out, hypothesis testing is like the heart and soul and even the mind of statistics. In fact, it can be argued that hypothesis testing is the whole purpose of statistics. That at the end of the day, when you run an experiment, you're analyzing the data through the lens of a hypothesis test. And it's exactly what it sounds like. You're going to be making hypotheses. We're going to look at the exact terminology. You're going to have something called a null hypothesis, which is also a status quo assumption about the nature of something as it is right now. You're going to have an alternative hypothesis, which is the challenger to the null hypothesis. So let me just dive in. Why listen to me talk when you can have a nice visual that will guide what I'm saying? So the language of hypothesis testing. So we need to establish some language. Hypothesis testing is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more populations. I mean, that's just huge. This is, you're testing something. This is actually, if you think about the process of statistics, if you think about running an experiment, what you do is you actually start by making your hypotheses, right? If you remember kind of like in elementary or middle school, they talked about what I talked about. They call it the scientific method, I believe. And, the scientific method has come under fire, but it's still, a general format you can use to test something about nature. And the scientific method, you got to pretty much start with, you do research and then you form a hypothesis. So you don't actually go collect any data or run any analysis until you've made a hypothesis about what you're doing. Well, we're just going to call them two hypotheses, the null and the alternative. So you start by making your hypotheses. Then you go out and you collect your data. You design an experiment that's a good experiment. You make sure you use all good sampling techniques to make sure you have randomness and all that business. So we talked about that, simple random sampling and cluster sampling, whatever you would say is most appropriate. You collect that data, then you analyze that data. And when you analyze that data, you finish off your hypothesis test. So let's talk about it. You have three really basic steps. Make a statement regarding the nature of the population. Make your hypotheses, in other words. Collect your data, analyze the data appropriately. You're going to have to run some calculations. You might calculate something called a test statistic. Then you might calculate something called a p-value based on the test statistic. There's going to be two types of hypotheses that you have to make at the get-go. You have to make a null hypothesis, H naught, oops, how cool it underlined it. You have to make a null hypothesis. We call that H naught or H0. It's literally a capital H with a subscript of a 0. It's the null hypothesis. It is a statement saying that there's no change, that there's no effect, that whatever you're looking at has no real effect on what you're doing. In other words, you're assuming that whatever phenomenon you're trying to measure or you're trying to prove exists or doesn't exist, you're assuming that it doesn't exist. That is the null. That is the status quo. What you have to do is you have to go out of your way using data and evidence to prove that this phenomenon does exist. So you start with a null hypothesis that says, no, it doesn't exist. And then you set out to either disprove the null or what we say reject the null hypothesis, or you then say, well, we haven't collected or we don't have enough evidence to reject the null. It is the assumed true hypothesis. It is the status quo hypothesis. And that's very important terminology. That has a lot of roots in Greek philosophy. Because Greek philosophy, especially, you have the big three in Greek philosophy. You have Socrates, you have Plato, and Plato is just, it's been said that all philosophy done since Plato is just footnotes of Plato, because Plato did everything. He was just one of the most accomplished, he is the most accomplished philosopher of all time, and he died thousands of years ago, which is really neat if you think about it. If you really think about that, even with all our modern technology, all the changes we've had over time, all that we have built upon Plato, and we have built upon it, still, at the end of the day, no one has quite accomplished what Plato accomplished thousands of years ago. That's really cool. And then you had Aristotle, who followed Plato. And Aristotle is also quite accomplished, maybe even the second most accomplished philosopher of all time. They kind of developed this basic framework. They argued that there was a status quo, and that in order to disprove the status quo or the nature of things as they are right now, you had to have a ton of evidence. You had to have a lot of information, evidence, data, whatever it is, observations about the natural world, they might have called it, because I don't think they were out there collecting heavy amounts of numerical data. They probably did some, but just not at the level we can today. But the basic framework has existed for thousands of years. We assume it to be true. Now, what we do is we also formulate the alternative hypothesis. This is the one that is directly disputing the null hypothesis and says it is not true, the null is not true. What you're trying to do in an experiment, what you're trying to do in a hypothesis test, you're establishing your null and your alternative. Now, ideally, what you're going to say is that you've found enough evidence, you've gathered enough data, run the numbers, you've found enough data to reject the null hypothesis in favor of the alternative hypothesis. But if your data does not support the alternative hypothesis, we don't turn around and say, oh, well, we reject the alternative and accept the null. That's not quite the wording. What we say is that the status quo could potentially be rejected. We just don't have enough evidence or data in this particular experiment to do so. So we're going to keep going with the null hypothesis, whatever it's going to be. Imagine, let me think of a somewhat interesting example. Imagine you wanted to talk about the height of the average American. So you say, oh, the height of the average American, let's say you're focused in on males. Let's say you were supposing that over the last 100 years, American males have grown 5 inches taller on average. And let's say we're even just focusing on adults. Think about that for a minute. 100 years time, and American males are 5 inches taller on average than they were 100 years ago. That's actually pretty impressive. It's not saying a child is now 5 inches taller. Yeah, that's just part of the normal growth cycle. I'm talking about an adult male 100 years ago on average is 5 inches taller today. That's kind of ridiculous. You might not believe that at first light. So in that particular analysis, your null hypothesis is going to be that the average American male height has not changed. You're going to assume that whatever phenomenon you're tracking is not actually happening. You start with that basic assumption. Your alternative hypothesis then would be that that change has happened, that yes, it is indeed 5 inches. What you're going to do then is you're going to have to go collect evidence. You're going to have to collect a random sample of heights of American male men 100 years ago, which I'm not saying that's going to be easy. Who knows how you'll get that data? You don't have a DeLorean time machine like I do. You can't just go back in time and collect it randomly. So you're going to have to use some recorded data, which may or may not be perfect. You didn't collect it, so you can't say it's good. And then you would go and collect some data today for American adult males randomly, and then you could test your hypotheses. So that's a great example right there. Again, the alternative hypothesis is either something that's going to be shocking or perhaps a bit thought-provoking or controversial because it's not just everyday stuff. So we're trying to find evidence to support the alternative hypothesis. Now, for our purposes in Chapter 10, we're only going to look at 3 different types of hypothesis test. There's a certain parameter we're testing. The only 2 parameters we're going to care about are the population proportion, P, and the population mean, mu. We're literally, section 10.2 is going to be about the proportion. Section 10.3 is going to be about the mean, mu. But no matter what, our basic framework, there's only going to be 3 types of tests. You could have the two-tailed test. Your null hypothesis is going to be that your parameter is equal to some value, whatever value you're testing. The alternative hypothesis is that the parameter is not that value. So if you want to see an example of this, let's say you're testing whether or not the average American adult blood pressure is 110, the first number, and the systolic blood pressure. Look, I don't know. So what you're going to do is you're going to test H naught. You're going to test that mu is equal to 110. This is just one example. You're going to test that against the alternative hypothesis, which is to say, no, the average American adult blood pressure is not 110. Now, I know that doesn't sound particularly shocking or fun. It's not like we're going on the Maury show and, the shock value here or something like that. And everyone's jumping up and down and screaming. Okay, yeah, this isn't sexy per se, but it is an example of a hypothesis test you might run. Another example of a two-tailed test, we can test for a mean of values, or we could test for a proportion. Maybe you're testing whether or not the proportion of votes that a certain candidate gathered in a given election is 0.57. And then you could test that against the hypothesis, the alternative hypothesis, that it's not 0.57. And again, may not sound sexy, but that is the proper setup. Every hypothesis test you run, you must perform your setup at the beginning, your null and alternative hypotheses. It is not just an annoying requirement. It helps you. It helps you so much more than you think once you see the process go down. Because you need to have your framework established at the beginning so you even know what the heck you're testing. You know what the values you're going to be using in your calculations will be. So every hypothesis test you run in this course, you will need to state your null and alternative hypotheses at the get-go. So that's an example of a two-tailed test. It can be for some parameter, either the mean, mu, or the population proportion, p. Your null hypothesis is always going to be a statement of equality. The null hypothesis here is that the parameter is equal to some value. The null hypothesis here is that the parameter is equal to some value. For a two-tailed test, the alternative hypothesis is not equal to statement. For a left-tailed test, the alternative hypothesis is that the parameter is less than left-tailed. Because when you're less than something, you're looking to the left of it. Oops, just this one. And then finally, if your parameter, if you're testing if it's greater than some value, greater than is going to be right-tailed. Because if you're talking about being greater than, you're looking to the right of something on a number line. The reason this one's called two-tailed, if your alternative is not equal to, you're looking at both the left tail and the right tail, both the less than and the greater than. So that's why it's called two-tailed, if you will. So this is going to be the framework. We are only going to run these three types of tailed tests, and the only two parameters you could insert there are mu for the average or p for the proportion. Let's practice. Let's try practicing this a little bit. We just need to write down the hypotheses. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. The researcher didn't say, oh, it's greater today, more Americans are volunteering. The researcher didn't say less Americans are volunteering. The researcher said different, that it's just not the same as it was. It ain't as good as it once was. So our null hypothesis, always going to be a simple statement of equality. We're talking about a proportion. We're talking about the percentage of Americans that volunteer for charity work. So our parameter is going to be P, and our null is always going to be equals to, in this case, 0.62. We're going to write it as a decimal. Since the researcher is testing if it's different today, our alternative hypothesis is going to be a statement of not equal to. And so this is a two-tailed test. What that's going to mean is that we are looking at a rejection region, which I'll define that later, that is in either tail, that is in two tails. Let's finish this page up. According to a study, my beard is stubbly, but according to a study published in March 2006, the mean or average length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. I would argue it's decreased because people just text more than they used to. But then again, more people have cell phones today than they did in 2006. So whatever, it's what the researcher believes. We're just going to write down that researcher's alternative and null hypothesis. The null, H naught, we're talking about the mean length of a phone call. So we're talking about the average, or mu here. Now, we're testing for the population parameter. Whenever you go and collect a sample, you're using sample statistics. So X bar is still going to be in play. It's like mu is the thing we're looking at theoretically. X bar is the practical numbers that we have. Our null is always going to be a statement of equality, and we're just testing whether it is equal to 3.25 minutes, or if today it has increased and is now greater than 3.25 minutes. This is a right-tailed test. Our rejection region, we're only looking at greater than. So what we're going to see is that we're only looking at the rightmost tail, because we're going to have to relate all this to a probability distribution. There's just no escaping that. Can't escape your fate. So there you go. And again, you must declare these. Now, the rest of this problem, if you wanted to run the full hypothesis test, after kind of this initial statement of what's going on, then you're going to look at the data itself. An actual study has to be taken under, and sample statistics have to be collected. But we're not doing that. We're just trying to set up the hypotheses at this point. Last one. According to the CDC, 15% of American adults experience migraine headaches. That's probably pretty true. Stress is a major contributor to the frequency and intensity of the headaches. A massage therapist feels that she has a technique that can reduce the frequency and intensity of migraines. Reduce. She says she can reduce the frequency. She can reduce what percent of Americans have them if you just use the massage therapist's system, or let her, I don't know, give you a massage. So our null hypothesis is going to be that the proportion, because this is clearly a proportion, we're not talking about an average, that the proportion is 15.2%, or written as a decimal, 0.152. The alternative hypothesis then is that with this massage therapy, that number can be reduced. So this is now a less than test. You're saying less than. In turn, this is then going to be a left tail test where your rejection region is to the left here. Let's use green. Left tailed test. All right, that's all I got for you. Remember when our final exam is? It's going to be Monday, December 14th. We are going to meet in person in our usual classroom. Unless you are ill, especially if you have COVID, you'll need to bring your laptop and your power supply. And we'll meet. We'll have ourselves a little stats party, and then we'll call it a day and a class as well. So I'll see you guys in Zoom on Monday, this upcoming Monday. And we'll focus on chapter 10 next week. Let me also